that.
Yeah, thanks. Thanks for inviting me and giving me actually the opportunity to present our recent results within the framework of your seminar. And I think I want to start first to introduce the team. So we have a close theory collaboration with a group of Ludwig Mattei and his PhD student, Tim Skulke. He simulate a lot of our experiments and helps us to understand a bit more into detail our results. And Jason Cosme, he was a former postdoc of Ludwig, so we're working together since many years, and now he moved to the Philippines and started his own group. From the experimental side, Andreas Hemmerich is the head of our group, and we have two PhD students, a senior PhD student, Christoph Georges, and a new PhD student, Padamon Korambut. So this is the team, and it's very nice to work here and collaborate. Yeah, and here in Hamburg, because we have a lot of theorists and experimentalists. Usually, the communication is quite fast. Unfortunately, at the moment in the pandemic is a bit more difficult. So, the title of my talk is Dynamical Phases in an Atom Cavity System. So during the past years, we realized many experiments and published proposals what all we can do. Even the transition from the normal phase to a self-ordered phase in our atom cavity system is a dynamical phase transition, and so on. What I want to focus today is about our recent preprint, which shows the observation of a dissipative time crystal. And so yesterday, before my talk, I just searched in the internet what people think about what a time crystal is. And I came up with this slide. So there are even in the 80s already the movies called Time Crystals, or everything of this goes a bit more in the direction of science fiction and has not really to do what we as a physicist understand from time crystal. But the bird and the idea was even maybe a little bit before 2012, Frank Wilczek came up and introduced the idea into physics. So let's go to Frank Wilczek's idea. It was actually, he asks a question, are there systems in our nature which spontaneously break time translation symmetry, and important is in its ground state, and it need to be a closed system? This is then analog to the formation of a crystal in space. And how can we realize such a time crystal? I have to say, no, we cannot. It's impossible. It does not exist in our nature. There were some no-go theorems published, but what is possible? So what is possible is like we can show them time translation symmetry breaking in driven systems. So realize something like an excited state time crystal. In most of the cases, we want periodically drive a system, so breaks the continuous symmetry already into a discrete one, and then breaks this discrete symmetry to realize a discrete time crystal. So it's a little bit like a loophole, I think. And Nature once, in one of the articles, it was written, they found a loophole to realize time crystals. It's a bit like if you think in a solid state system, you offer two sublattices, and the system in the end picks one of it. And for which one the system decides is triggered by quantum fluctuations. This is the idea of this kind of systems. It was already observed in the group of Chris Monroe and Michael Lukin, so these were the first two. And shortly after, Peter van der Straten realized discrete time crystal as well. Due to their periodic driving, this leads to a subharmonic response, and they demonstrate spontaneous breaking of a discrete time translation symmetry. So in all these cases, what was limiting is actually the dissipation, so that this is not a perfectly closed system, that they introduce some energy into the system. And what we then came up, or was not originally our idea, it was already there were some theory proposals by Masahiko Ueda and even before by Shitra, that in a dissipative system, one can realize a discrete time crystal as well, and it is stabilized by this dissipation. So in the end, what happens is like you have an energy flow through the system, which is then continuous, but still, and in the system, somehow stabilized by this. So how does our experimental system look like? This is what I want to introduce first, because yes, you need to know about what we are working with. So if there's anything not clear, or if it is too boring for you, because I've heard that most of you are serious, so just interrupt me and let me know if I have to explain a bit more into detail, or I should just skip it. So what we are working with is a BEC of rubidium-87 atoms. We overlap it with the 0,0 mode of our optical cavity. A small sketch is here on the right side, so the BEC in the center of the 0,0 mode. And we pump our system in all the experiments with 803 nanometers, with a wavelength of 803 nanometers. That means we are in the dispersive regime and far detuned of the atomic resonance. Our cavity has some unique feature if you compare it to most of the cavities in the world, that the distance between the mirrors is almost 5 centimeters, so it is quite long. The photons get lost in the cavity because the mirrors are not perfect, or you have some surface roughness. So if you have a long cavity, the light spend more time in vacuum than until it hits the mirror, and this leads to a small field decay rate, in our case of 4.5 kilohertz. In the many other experiments, it's 50 times higher. The recoil frequency in our system for rubidium atoms pumped at 803 nanometers is 3.6 kilohertz, and it is the same order of magnitude as our field decay rate. This is what we call recoil resolution, because due to the narrow bandwidth of our cavity, we can resolve a single recoil energy. This leads then to a very interesting situation where the cavity dynamics and the atomic dynamics has the same time scale. So it is not like in many other experiments where the cavity field adapt instantaneously to the atomic distribution. In our case, it leads to a retarded infinite range interaction between all the atoms. And this leads to a lot of non-linear physics and subharmonic period doubling and all you can imagine. Our experimental accessible observables I present next, because this is what we can measure. So what we can measure is, unfortunately, the resolution of our imaging system is not good enough to really detect directly the density distribution. But what we can do, we can apply a time of flight method and measure the momentum distribution. That means we switch off all trapping potentials, and due to a free expansion, the momentum distribution is converted into a spatial distribution, and then we take an image of the sample. Basically, we take the shadow of our atoms, what looks like here. I put one measurement, one single shot here on the right side. Now, what we get from this image is like we get the distribution, so the amplitude of the momentum distribution, but we don't get the phase. So we get information about the periodicity of the system, but not about the phase. So the phase information is lost. Luckily, we are working with a cavity. So the cavity light field gives us another way to extract information of the system. So for example, as I told you, the mirrors are not perfect. We put there a single photon counting module which detects the photons. So here's a typical data, and each blue bar is something like a click, most of the people say. So it is the detection of a single photon. And this event information gives us access to the statistics and the number of photons inside the cavity. In addition, we have implemented a balanced heterodyne detection. And with this detection, we can access the field amplitude of the intercavity field, so the intercavity photon number as well. But what you see here, a typical data is here on the right-hand side, so the blue curve, and so actually both data are from the same single shot. And you see that the signal to noise is much better from this balanced heterodyne detection, because we overlap the light leaking through one of the mirrors with a strong local oscillator to amplify it. Unfortunately, we lose the event information. So if you want to access the statistics, we still need to use the single photon counting module. But if you're just interested in the amplitude, we better use the heterodyne detection. And another advantage is that this local oscillator, what is our phase reference, has a fixed phase relation to our pump. So if we beat it with the cavity field, we can extract the phase difference between our pump and the cavity field. And this is plotted here in red. If it is oscillating between -pi and +pi, that means just there is no light field in the cavity and the phase is practically not defined. If then we have an infinite light field in the cavity, the signal gets much narrow and we can detect this phase difference. This is important because most of our experiments, we are using the data from this heterodyne detection, and especially this phase data is very important. About the pumping scheme, what we are using, we produce our BEC, overlap it with the single mode of our cavity, so we transport it into this mode, and then we pump transversely with a standing wave potential, basically an optical lattice, and we can tune the depth of this optical lattice. If we exceed a critical pump strength, the atoms can decrease their potential energy by self-organizing in a checkerboard lattice and scattering resonant photons into the cavity. This was first observed in the group of Vladan Vuletic with thermal atoms, and in the group of Tillmann-Esslinger with BEC. So to describe the theory of a system, so the theoretical description, the Hamiltonian that describes our system consists of 3 parts. So we have the cavity field part, we have the atomic part with the kinetic energy, the trapping potentials. We can also add a contact interaction term as well. But the most important, most interesting is the atom cavity coupling. The atom cavity coupling is basically the overlap of the distribution of the atoms with the pump and cavity field. And we have here this is a intercavity field term, and then the second is accounts for the scattering from the pump into the cavity and vice versa. And here I draw with red, though the pump strength. So this is what basically the depth of our optical lattice. This we can tune in time. And what in addition we have now implemented in our experiment, but I cannot show the results today because we are a bit limited in time, is that we can modulate the phase. So we can shake our lattice like this, so we can modulate the amplitude, and we can even shake our lattice. So what happens?
Sorry, can I ask a question?
Yeah, sure.
What is epsilon P of t here? You said it, but I was
sorry, what is what?
Epsilon P of t.
This is the field amplitude of the pump field of the transversal standing wave. So what happens in the end is like we scatter photons from the pump into the cavity and vice versa. Each time there's h bar k momentum transferred in the direction of the pump and direction of the cavity field. So this leads to a discretization in momentum space. So we populate basically these momentum modes. So the 0-0 mode is the BEC mode. And if we enter the self-organization phase, then we populate this ±1 h bar k mode. So these four modes. The other modes indicate the pump lattice and so on. But this tells us that we can simplify our model, and in most of our simulations we did, we can use a momentum mode ansatz. So that means like our matter wave field, we develop in plane waves in momentum space. We found out that we get a quite good qualitative agreement if we neglect the trapping potential and collisions, and we neglect as well the quantum fluctuation of the matter wave and the cavity field. And with this simple mean field simulations, we can even do by ourselves, because we are just experimentalists, helps us already to understand most of our experiment at least quantitatively. If we need a more sophisticated model, luckily our colleagues helped us and implemented a truncated Wigner model. This adds a stochastic noise term, which accounts for the dissipation of the system, so of the field decay, and it samples the initial momentum distribution, so the initial quantum fluctuation of the momentum distribution, so of the matter field. They can include a trapping potential, two-body collisions, and if we want, they can even add a decay of the atom number, what accounts for three-body losses in our system. And with this truncated Wigner model, we can then understand quite good the quantitative results of our experiment, why, for example, the oscillation in our systems of the dynamics is somehow damped out. And there, the truncated Wigner simulations help us a lot to understand them. There's now one last thing, and then I'm already finished with this kind of lengthy introduction. So there are two detunings in our system. So there's atom pump detuning. That means like the detuning of the pump with respect to the atomic transition. And in all our experiments we have performed so far, it was always red atom pump detuning. So that means the atoms are high field seeking, so the minimum of the potential is at the maximum of the intensity. That means if the atoms self-organize and localize, they localize at the maximum of the intensity and they see even more light, the coupling increases and this process gets amplified. If we are switching on the blue side of the atomic resonance, and I will talk a little bit about this in my outlook, because this is what we plan to do in the future. I hopefully this month, not this month, I think next month or the month after, we want to start with the atoms are low field seeking. That means the atoms localize at the minimum of the intensity. So if they start then to self-organize, to decrease their potential energy, and they don't see the cavity field anymore, so the coupling decreases and everything breaks down, and then it starts again from the beginning. And in this kind of systems, before Francesco Piazza and Helmut Rich in a 1D system, and we with 2D simulations proposed limit cycles. And then if we go a little bit further, this limit cycles, the phase of the limit cycles depends on the initial condition and so on. And yeah, we hope that we can show a continuous time translation symmetry in this kind of system. The second detuning is a cavity pump detuning. So here on the left side, I draw our cavity resonance. The x-axis is frequency and the y-axis is the arbitrary amplitude. So for all the experiments and simulations, everything I'm talking about today, we were using negative, so red cavity pump detuning. There we have elastic scattering is happening and we observe the self-organization phase and enter at density wave phase. So this is for all the experiments and everything what I do today. We are on the red side and the lower frequency side of our cavity resonance. We perform some experiments on the blue side as well. There we observe matter wave superradiance similar to the experiments of the group of Wolfgang Ketterle. In our case, we can use our narrowband cavity to steer them. But yeah, I don't have time to talk about this today. So these are the detunings, and now I'm finished with this introduction and come to my outline. And my outline starts, so the rest of my talk I will talk a little bit more about the self-organization phase transition, because this is the starting point of all the simulations and experiments and everything I show after. Then second, the main part is about the observation of our dissipative time crystal, and if there's some time left in the end, I would like to show you what happens on the blue side of the atomic resonance, or what we propose or hope to see there. So the self-ordered phase transition is actually the starting point of the experiment, as I told you. So in this slide, maybe you remember, you saw already today, that we pump our BC transversely with the optical lattice, then we increase the depth of this optical lattice and the atom self-organize above a critical pump strength. So what basically happens, because we are far detuned for the atomic resonance, is Rayleigh scattering. For homogeneous BC, you can think that for each scatterer, you find another one with the right distance so that both scattering events interfere destructively. So the Bragg condition is not fulfilled. If the atoms self-organize in this checkerboard lattice with a distance of lambda, this fulfills the Bragg condition, and the scattering from the pump into the cavity and vice versa is constructive. So, and due to the buildup of this 2D optical potential, the atoms can decrease their potential energy. But there are now two degenerate states that would fulfill this Bragg condition. So what they are shifted by lambda over 2. So one I draw here with the blue filled circles, and one I sketched with the non-filled circles. So it's the same periodicity, but shifted by lambda over 2 in space. From our time of flight images, this would look like this, the self-ordered phase. So we populate the plus minus 1 plus minus 1 H bar K mode. So these 4 modes, which accounts for the lambda periodicity of our system, so for the checkerboard lattice structure. But as we only know the amplitude of this momentum modes, we don't know anything about the position in space. So we cannot distinguish these two states. So how can we distinguish? Yes, we can, and it was observed already first by Vladan Vuletic with thermal atoms, and in the Esslinger group with the BEC. So this is nothing new, and it's nothing we invented. We just repeated it because we need it for the observation of our dynamical phases. If you can think about the atoms localized at the blue sublattice, so the blue lattice side, so let's call it the even lattice, and scatter photons. And if you compare it to the atoms localized at the red spots, the phase of the cavity field is shifted by pi. And if we now measure the phase difference of the field leaking out of the cavity, so the phase of the intercavity with respect to the pump field, we can distinguish these two states. There's just one technical problem. So the experimental cycle, so the BEC production, takes about 50 seconds. And the stability of our phase reference is only a few hundred milliseconds. How can we overcome this problem? We just compare two realizations within one experimental cycle. And now let me take a bit of time to explain this plot, because this is how it will look, everything I show you in the rest of my talk, and from there we extract all the information from our system. So the upper panel show the depth of the depth of the pump lattice in time, and the lower two panels show blue. There's the phase difference between the pump and the intercavity field. So if there's no intercavity field, it oscillates over the full 2 pi, or better, it jumps, not oscillates, so the phase is not defined. If we have a finite intercavity field, the phase signal gets much more narrow, and we can detect the phase. The red signal here, what you see is the intercavity photon number. So this is the amplitude of the intercavity field, and the blue is the phase. And if we enter now the self-ordered phase, we measure the phase difference between the pump and the intercavity field logs to 0, and then we leave, and then we enter again. And for the second realization, for example, we measure exactly the same phase. What else could happen? We measure two different phases, so 0 and pi. And these are basically the two symmetry broken partners in this self-organization phase. So this accounts for the two sublattices. Now we want to show that this symmetry, what is important for the rest of our experiment, is well established in our system. So we repeated this experiment about 400 times. And if it is just triggered by a quantum fluctuation, so it is completely random if it picks phase 0 or phase pi, we would expect for both cases to happen equal probably. And this is the result. So on the x-axis, you see the phase difference between the first and the second realization. And there you see a maximum around 0 and a maximum around pi. And the y-axis shows the relative counts. So we can clearly distinguish between the two cases. So either we have a phase difference of pi, or we have a phase difference of 0. And if we sum over all the events for a phase difference 0 and for phase difference pi, we end up with this ratio. So 53.5 to 46.5. This is close to 1 and tells us that the symmetry is well established in our system. Okay, you can say you would expect 50-50. I think we could improve if we do more measurements, maybe. But if you compare it, for example, to the experiments published in the group of Tillmann-Esslinger, they have a much worse ratio. They have something like 60-40 or so. Okay, so this is what you need to understand, that we have these two sublattices and we can distinguish by measuring the phase difference. So let me then summarize this part about the self-organization phase transition. So we observe a phase transition from a BC to a self-ordered phase, and the atoms self-organize in a checkerboard lattice structure and decrease their potential energy by resonant scattering or constructively scattering photons from the pump in the cavity and vice versa. Second, we can observe that Z2 symmetry breaking. There are two generate states in our system, so two different possible sublattices which fulfill the break condition, and we can distinguish between them by measuring the phase difference between the pump field and the intercavity field. And what is important now, that the simulations show us that the quantum fluctuations already the quantum fluctuations trigger or decide which of the two sublattices the system picks. And this also due to the initial conditions, you see where the phase transition actually happens in time. So this varies by about 10% due to different initial conditions as well, due to the noise and the fluctuations of the cavity field and the matter ray field. And by repeating this experiment many times, we observed that the Z2 symmetry in our system is quite well established. So now I'm finished with this self-organization part. So this is what is important to more or less understand, that we have these two sublattices and we can distinguish by measuring the phase. This is actually what is the take-home message of this section of my talk. And and with this you can then understand, I think, the rest what I will show you. So are there already any questions, or if not, I would just continue. It doesn't look like this is the case, so let me just continue. So what I wanted to present you is now our recent observations of a dissipative discrete time crystal in this kind of systems. So for this, we modulate the amplitude of our pump lattice. That means technically in the experiment, we vary the intensity of the light field creating our pump lattice with a frequency omega d and a strength f0. Here's a sketch why this intensity modulation leads to a subharmonic and a period doubling subharmonic response of our system. So the y-axis is the potential energy and the x-axis is the time. So at the beginning, we produce our BC in our harmonic trapping potential. Then we ramp up our pump lattice and cross the transition from the normal to a self-ordered phase. At T0, then the system is well within this self-ordered phase. And here I choose one of the sublattices. So I say, okay, it is now starts to be in the even sublattice. This could be on the other side as well. But now, okay, let's say because I know there are two potential energy minima, so the even or sublattices, and the system picks due to an initial fluctuation, the even sublattice. If we then start to modulate the intensity, the system goes back into the normal phase. So we basically decrease the intensities of the pump strength. So the system goes back in the normal phase. And after one driving period, we cross the phase transition again. And then if we do it with the right frequency and the right strength, the system then enters the self-ordered phase, but on the symmetry broken partner. So it localizes in the other sublattices. And if we do this again, wait another driving period, the system is back in the even checkerboard lattice. So that means in the initial condition, the same as at T0. So the system repeats itself in time after 2 times the driving period. So what we observe, a period doubling and a switching between the 2 symmetry broken states with half of the driving frequency. So let me show you now how this looks in our, how we can see this in our experimental data. Here's the same plot as I showed you before. So the upper panel is the depth of our pump lattice. The second panel is the heterodyne data. So blue, the phase difference between the pump and the cavity field, and red, the intracavity photon number. So first we produce our BC and load the BC in an optical lattice. Here you see the momentum time of flight image, or the momentum distribution. We see 2 peaks at minus 2 h bar k and plus 2 h bar k, which indicates the 1D optical lattice. Below, I show the single particle density calculated using our mean field model. So it just show a plane wave. If we now cross a transition to the self-ordered phase, we have a finite cavity field, so the phase is not oscillating anymore and locks to 0. In the momentum distribution, we populate the plus minus 1 h bar k mode. So these 4 modes, which indicates for this lambda periodicity in our system. And if we use this momentum picture and the phase we get from our heterodyne detection, we can calculate what is the in which sublattice the atoms are, and in this case it is the even sublattice. So this is how the single particle density looks like in space. This momentum space, and below we have real space. If we now start to modulate, the intercavity field rises, but the phase stays at the same. So that means the atoms just localize a bit more, but they stay in the same sublattice. If we then continue a little bit further, the intercavity field drops to 0. The phase is not defined and jumps between 0 and 2 pi basically. And if you have a look on the momentum distribution, it looks very similar as in our, or it looks actually the same as in our normal phase. So we have the BC in a 1D optical lattice, and the single particle density is just a plane wave. If we wait a little bit longer, we see the population of the plus minus 1 h bar k modes in the momentum distribution. So that means we have now our self-organization again, so a lambda periodicity in our system. And if we have a look on the phase now jumped from 0 phase difference to pi. And from this, we know that the system switched to the symmetry broken partner. So in this case, to the odd sublattice. And here's the single particle density again. And now the atoms have localized in the other sublattices. So in space, it is just shifted by lambda over 2. And if you can continue now this modulation, the system switches back and forth between these 2 symmetry broken states. And in the end, it repeats itself. So it's back again in the, we measure a phase difference of 0 again, and it's back in the even case after twice the driving period. And then we can observe this oscillation. So we observe a period doubling in our system. What is not that special, maybe it is nice for this kind of system, but in the end, it is nonlinear physics. And you have this in, you can observe similar things in many other systems. So what I want to show you now is how this breaking of the Z2 symmetry in space leads to a time translation symmetry breaking. So as I told you, the system can pick either the blue or the red lattice sites. And so that's the 2 possible sublattices in space. And by entering the self-ordered phase, the system picks one of them. This relates on the time axis. If we then start to modulate, it either starts at the even or at the odd sublattice. So it oscillates even, or odd, even, odd. And this is so the time phase between these 2 realizations is then shifted by pi. So what show the 2 symmetry broken partners of the time translation symmetry. We can observe this in the experiment as well. So we enter the self-ordered phase, start to modulate, leave, enter again, start to modulate again. And what we observe is like first we have one phase and then it starts to oscillate. Then we leave the self-ordered phase, we enter again, we observe the same phase and starts to oscillate. So the phase difference is zero. So the time phase difference is zero. And the phase difference of the intercavity field with respect to our pump field has the same value as well. But what else can happen that we start here with in the even case, and then the second realization is odd. So if you compare these two signals, they are phase shifted by pi. So the time phase is shifted by pi. So what we realized, or I show here, these are then the two symmetry broken partners of our time translation symmetry. Now, let me show you a little bit what happens if we change our modulation frequency, modulation and strength, so the modulation parameters, to show you that the system or the subharmonic response and this period doubling is robust against change of these parameters. So the x-axis is the modulation frequency, the y-axis is the modulation strength, and the color code shows the relative crystalline fraction. So what we calculated here, we detect or we measure the signal of the phase difference, calculate an FFT and take its amplitude at half of the driving, so at the subharmonic amplitude divided by the maximum subharmonic amplitude we measure in this full parameter space. What we observe that for a quite large area in our driving parameter space, we observe this quite stable period doubling. Let's now have a closer look. We fix the frequency to 4 kilohertz or slightly above 4 kilohertz and increase the modulation strength. So for weak driving, the system just stays in the same sublattice. And if we calculate the FFT of this phase signal, what is shown left, and on the right side, the FFT, there's no significant peak, so it is basically flat. Just a little bit of noise is visible. If we now increase the driving strength, we see that the system switches between those two sublattices and we observe a significant nice subharmonic peak. If we increase the driving further, the system gets very chaotic. So what you see here on the left side is single shot data. So it looks each time very, very different. This time it's stuck somehow in one of the two phases, but it can be any all non-periodic behavior we have seen. So each single shot is basically different. And in the FFT, we don't see a subharmonic response anymore. So I showed you that.
Can I ask a question before you?
Sure.
So in these examples, you always eventually have a dephasing, a decay, for example, in the middle, in the middle plot B. So what is it that, or a width, of the FFT. So what is it that sets, what in your experiment is it that sets this decay time scale or the width of the FFT?
Yeah, so this is atom loss. I will somehow try to convince you with some truncated weakness simulations where we implemented atom loss. We can, because in the experiment we cannot switch it on and off, and even contact interaction plays a role. So yeah, this is in the end what limits our lifetime. So I showed you that this subharmonic response, this period doubling, is robust against change in the driving parameters. What else we can do? We can add some noise on our modulation signal. What we did, we add some white noise with a bandwidth of 50 kilohertz on our modulation signal. So as before, we modulate with just a very nice sinusoidal signal, and this is what you saw already before. And now we add a little bit of noise. So you see that this is directly, so we measure directly the depth of the lattice. This is directly what we apply to the atoms. And if we add a little bit of noise, maybe the lifetime is a bit reduced, but it looks very, very similar. If we go to intermediate noise, so increase some noise strength a little bit, it die out a little bit earlier, but in the end, it looks still quite similar. Maybe the pulse is a little bit more irregular. But if we go to strong noise, so you could even not really see or can see by eye the modulation frequency anymore, then the system starts to get chaotic. So for example, here the phase is not switching, it got stuck. We see at some time, for some time, some switching, but it's already close to or in this chaotic phase where we don't observe a stable subharmonic response. We repeated this experiment for different noise strengths, and what is plotted here on the right side, so the subharmonic amplitude against noise strengths, and it for increasing noise it drops, but it survives quite some strong noise. For example, here it looks already very noisy already by eye, but we still see nice subharmonic response. Now we repeated this experiment for the full phase diagram for all.
I ask a quick question. Sorry.
Sure. Yeah.
Sorry again. Why is it that you get stronger, a higher fraction for slightly, higher than zero noise? Is it?
And do you talk about this point?
Yeah.
Actually, I think this is due to some measurement error. You see that the error bars are much larger than for the others. So I would not say that we increase because of noise. I think this is just an usual fluctuation of our measurement. So I promised you to show you what happens with the full phase diagram if we add noise. So the x-axis is again driving frequency, y-axis is driving strength. And G, this phase diagram is the same as you saw already before. If we add a little bit of noise, it gets deformed, but we still have some nice area where we see stable period doubling. If we go to intermediate noise, this still shrinks this area, but it's still present. For a stronger noise, then there's almost nothing left. And if we go even further, it would be just white. So it is to some extent robust against noise, but yeah, there are limits of the system. Maybe, and this is the question that was already asked. So you see that there's even an exponential decay of the pulses of the intracavity field. Why is this the case? So for this, we ask our colleagues to run some truncated weakness simulations. They haven't used the trapping potential, so they were using periodic boundary conditions, but they included two-body contact interaction and atom loss. For no contact interaction and no atom loss, the system oscillates basically forever. So what you see here is like the intracavity photon numbers, so the pulses you saw before. Below is plotted the two-time correlation function that shows the subharmonic response of the system. If we add now a little bit of contact interaction, nothing has changed, at least as long as we can simulate, because at some point there's a limit of our computational effort we can do. But if we increase the contact interaction even more, that you see already here in this two-time correlation function, that after some driving periods, it's basically flat and the subharmonic response dies out. If we now add in addition atom loss as well, then you see that we observe this exponential decay of the intracavity photon number and also of the contrast of this two-time correlation function. And this looks pretty similar to what we observe in the experiment. That's why we think we are limited mostly by atom loss. The contact interaction for sure play a role as well, but I think mostly what first limits us is the loss of atom. So in the end, it is three-body loss in most of the cases in our system. So let me summarize this part just a little bit. So if we modulate the amplitude, this leads to a subharmonic response, and we observe a period doubling. This period doubling I showed you is robust against change of the driving parameters. And if we add artificial noise on our modulation signal, it still survives as quite some significant noise strength. What I haven't showed you, but what experiments we tried as well, so we also changed system parameters. So everything I showed you was done for the same atom cavity pump detuning. No, not atom cavity, so the cavity pump detuning. And we were using different cavity pump detuning, and we observed subharmonic response as well. So I hope this convinced you that we see or demonstrated some breaking of discrete time translations, of a discrete time translation symmetry, and our observations can be called a dissipative discrete time crystal. So this was the summary and end of this part. And now there's about a few minutes left. So, and I want to use them to show you what happens on the blue side of the atomic resonance. So this is what we plan in the future. Now everything started with a proposal by Helmut Ritsch and Francesco Piazza, where they observed in a 1D model on the blue side of the atomic resonance, or in a 1D model of the atom cavity system, they observed limit cycles. And we were setting up then a 2D model and had to look, can we observe this with our system parameters as well? So I was running mean field simulations without a trap, no collisions, no quantum fluctuations. And for fixed cavity pump detuning, we were ramping up our pump strength. And calculate the intercavity photon number. So the color code is the intercavity photon number. So this NP, as you saw before. X-axis is the pump strength and time axis as well. And the y-axis is the cavity pump detuning. So for fixed cavity pump detuning, we are ramping up our optical pump lattice and have a look how the cavity field, dynamics of the cavity field looks like. So if we stop here at this parameter tuple where I marked with 1 and observe and simulate for this parameters the intracavity dynamics for a few tenths of milliseconds and then calculate the FFT, we end up with this. So it's basically flat. So we observe a steady state intracavity field. So here's the FFT, x-axis is a frequency and y is an arbitrary amplitude. If we go in this more interesting region where you see already these oscillations, if we stop there and have a look on the cavity field dynamics, we expect to see a single frequency response on a very narrow frequency. So this is this limit cycle area. If you go a little bit further, so in this very colorful area there, we expect to observe some chaotic dynamics. So the system responds on many frequencies with a very broad peak, and each shot we expect to be different. To have a little bit a closer look, what happens, we also extract the frequency. So we stopped at each parameter tuple and simulate the intercavity dynamics. And what I plot here on the lower plot is the frequency response of the system. And there I pick the maximum peak. So, and if I picked, if I see just one peak and if I see one, and what is the frequency of it. And there, if, for example, I fix my cavity pump detuning and increase the pump lattice steps, I see an oscillation, a flat plateau, so the system responds with a more or less fixed frequency until it enters some chaotic phase. I can do the same for fixed pump lattice steps and vary the cavity pump detuning, and there I expect to observe plateau as well until we are entering this chaotic phase. So to understand this a little bit better, I ask Jason to perform some Tankett-Wigner simulations where it includes the noise, also the quantum noise of the matter wave field. So it samples the initial condition and accounts for the noise due to the dissipation. You need now to understand what I think I mentioned before already, that the phase transition from the normal phase to the self-ordered phase is triggered by quantum fluctuation of the cavity field and of the matter wave field. That means for each different Tankett-Wigner trajectory, so for different initial states, it should show a different phase transition, or the phase transition appears at a different time or pump strength. And here I plotted just randomly picked three different Tankett-Wigner trajectories. And you see, if you look on the frequency on the Fourier spectrum, the frequency is fixed, but the phase is shifted. So the time phase is shifted. And if you repeat this for many frequencies and plot as a in polar coordinates, we see that we basically all the trajectories are distributed over the full 2 pi. So what we expect if we realize this experiment, so for each single shot and for each realization, we would expect to measure a different time phase. If and we add some stochastic noise in our system, this gets spread even a little bit more homogeneous. And yeah, this if we realize in our experiment and can show that we observe really this 2 pi distribution of the time phase, we can then think about calling it that we break a continuous time translation symmetry, like in what is much closer to a real crystal, where the localization of the atom cannot be only at a discrete distance, but the crystal can start everywhere. So the first atom can be everywhere in space. So that means that in this related to the time translation symmetry means like the time phase or the oscillation when it starts, it can be any value. And now the time is more or less over, but I just want to show you this last slide and then I'm already finished. Or what we can do as well, we can do the same as we did before and drive our system periodically at close to twice of this intrinsic limit cycle frequency. And then we go from this slightly shaded and frequency slope of our frequency risk of the response of the system, we can lock this to exactly half of the driving frequency. So we see a perfect, in our simulation, we see a perfect subharmonic response. And it does, and this subharmonic response doesn't depend on the Tankei, on the initial conditions, which shows our Tankei-Wigner model. And in the simulation, we then basically, we saw and from the simulation that we expect both symmetry broken partners as well, but the frequency is completely fixed. What is not the case for this time independent drive. So the summary, so this is really the last slide. So for a time independent drive, so we just ramp up into the self-ordered phase and then hold our pump parameters constant in time. We propose to observe stable limit cycles, and due that the time phase of all this limit cycle of each realization should be different, we propose a breaking of a continuous time translation symmetry. And if we then start to periodically drive our system close to twice of this intrinsic limit cycle frequency, we observe a perfect subharmonic response and stabilize our limit cycles in frequency and also in the parameter space. Yeah, that's all what I wanted to show today. So thanks for your attention, and I'm happy to take questions.
I think Hans, it was a very clear talk. So does anybody have any questions? If not, I do.
Can I ask one?
Sure.
So, okay, I apologize beforehand if I missed one or the other aspect. So, but at some point you mentioned that there is damping, right?
Yeah.
And this is, I think, understandable that there is, but I mean, this is also a crucial point, right? In this time crystal phase. So whether there's, so to say, how can I say, damping due to the fact that there is, so to say, a fundamental issue, namely that it's not a crystal, but it has finite range correlations in time, or whether, so to say, if you were to do a better experiment, you could reduce these sources that give you damping, and then in principle could see an extended lifetime of this time crystal. This is, I think, kind of a central point, no? Because there are lots of things that oscillate and maybe damp at the end. But somehow there has to be some kind of closing of the gap, at least in theory, let's say, that makes these time translation breaking last forever. Is my question clear somehow?
Yeah, I think I understand what you were asking. So so first, in experiments, you have always, it's never perfect, so you always will have damping. But in theory, let me go back to one slide. So in theory, it would live forever.
Okay.
So this is the blue curve. in theory, it can live forever. So if we, for example, in experiments, you can reduce two-body contact interaction by using a Feshbach resonance and reduce this contact interaction, and we can increase or decrease the density of our sample. This is experimentally a bit difficult, but we can just open our trapping potential even further. What counts in the end is just the overlap with the cavity mode. But if we, along the cavity mode, extend it even further, it would not matter. And lower density means less losses and less contact interaction. If we go further and further, we expect longer lifetime. And this is what we observed in the experiment. We repeated this experiment for different transversal trapping potentials. So we were reducing our density, but basically our mean density by a factor of 5. And this increased at the beginning, the first measurements, we just saw 1 or 2 oscillation cycles. And then we noticed, oh, what is damping? And we said, yeah, probably some density effects. And then we opened our trapping potential, decreased the density by a factor of 5, and then we could observe 15 driving cycles. So
can I maybe ask a follow-up question now that you are, so to say, explaining all these kind of dirt effects? So there's also always this kind of characteristics that is kind of advertised, that this time crystal is robust with respect to perturbations. So how does this enter in the discussion here? So what would, you see what I mean? Because you could argue, well, if any small kind of dirt effect destroys what you see, that's also not good somehow for this to be a phase.
Okay, yes, that's true. That's true. But yeah, there are some. So I think this dirt effect or this robustness is in most of the case, but when people talk about it, should be robust against fluctuations, against quantum fluctuations. So the dissipation does not limit us. What you see, if we have for the blue curve, we have dissipation included. If we have this does not somehow limits the lifetime. What limits the lifetime is really like this, somehow this dirt effect, what is in our case, unwanted, contact short range interaction of the system. And so, but if you have a look and compare all the other experiments, they are all limited in lifetime. In the end, I think it doesn't matter much if you limit it to 15 driving periods or 50. In the end, for the physics, it is the same. It is just technically you can always get better and better. And if you would use, for example, strontium atoms, which has almost 0 S-wave scattering, then you can see like Bloch oscillation experiments where people observe thousands of cycles. They go on a Feshbach resonance, and if they have contact interaction, it dephases faster.
Okay, thank you.
You're welcome.
So while people ponder more questions, let me ask one.
Yeah.
Okay. Stop the recording.